In these sections, we are going to learn about types of functions. The objective of this subsection is to make connections between the algebraic equations to its name and to the graph. For example, if I mention quadratic equations, then you'll be able to plot the graph of parabolic curve on your mind. So as simple as that. To achieve that goal, there are 4 things that we are going to learn. The first is the definitions of function. Second is the f of x terminology. The third one is the names of functions, and the fourth one is the domain and range. So let's begin with the first one, the definitions of function. Function is defined as a set of ordered pairs in which each value of the independent variable, oftenly x, in the domain that has only one corresponding value of the dependent variable, which is y, in the range. So this may sound like a long statement, but I'll make it simple for you. This is a set of ordered pairs, which is like x comma y, in which one x value has only one y value. That's it. To help us to memorize this better, I'm going to highlight the keywords. A set of ordered pairs, it could be x comma y, abscissa or ordinate, in which each value of the independent variable has only one, and then corresponding value of the dependent variable. That's it. And to help us to get more understanding, I'm going to provide us the graph. Determine from these 2 following graphs which one is function or which one is not. So back again to the definitions of functions. For one x, there's one y. Then we can use what we call as the vertical line test. If we do the vertical line test on the first graph, then we can see there's an intersections over here, and the intersection happened only once. So 1x for 1y. This must be a function. Let's do it for the second example. If I do the vertical line test on the second example, then I will have 2 intersections, one over here and the other one is here. So this must not be a function. The conclusion, if you are given a graph, just do the vertical line test to know if this is a function or not a function. Let's move to the next one. F of x terminology. F of x is usually determined y, which is the dependent variable in the functions. So we can write it f of x is equal to y, or y equal with f of x. But why we use f of x instead of y? Because in the more advanced problem, when you have a graph and all the graph represented with the y, this is y, the other one is y, then we cannot tell which one y that it's mentioned unless we put it as this is a f of x or this is g of x. That's why we need f of x terminology. Now, to clarify our misconception, f of x is not f times with x. I'm going to put an example. Let's say f of x is equal with x squared plus 2x plus 1. Now if I have f of 4, then it will be 4 squared plus 2 times with 4 plus 1. So that will be 25. If I have f of a, then it will be a squared plus with 2 times with a plus with 1. So it's just exchange or substitute the a to the x and x value in this equation. If I have f of a plus 4, then it will be a plus 4 square plus with 2 times with a plus 4 plus 1. So then it will be a square plus with 8a plus with 16 plus with 2a using the distributive property plus 8 plus 1, and then we can make it simple as a square added with 10a added with 25. We come to the names of functions. So let's begin with the first one, polynomial function. The polynomial function has this general equation, f of x equal with a n x to the power of n and so on. So when you see these two graphics, this example of polynomial functions. Quadratic functions is also part of the polynomial function. And we can tell how many degree it is by the turning point. This is what I mean with the turning point. So you'll have the maximum and the minimum point. Sorry, this is the minimum point, the maximum point, and then the minimum point. So you have like 3 maximum minimum point. For the quadratic, it has only 1 turning point. So this is second degree. For the cubic functions, you can have like this 2 turning point. So this is the third degree. Or although it's not a guarantee, for the cubic point it can also be like this, which is 1 inflection point. But cubic point will not have more than 2 turning point. So you look at this one on this graphic again, you will have like 1, 2, and 3. So if you have like 3 turning point, this will be 4 degree. And if you look at this one, you have 1, 2, this is 3 inflection point, 4. So this must be the 5th degree. This is how we can tell the degree of the polynomial easily. Next one is the quadratic function. On the quadratic function, you have like 3 conditions. It can have no x-intercept. It has also possibility of 1 x-intercept or 2 x-intercept like this one. Now, the conditions can happen if you have, for the no x-intercept, d is less than 0. What is d? D came from the quadratic formula x1, 2 equal with negative b plus minus square root of b square minus 4ac over 2a. So for a glance, b square minus 4ac is what we know as d. When you have d value which is less than 0, then the solutions over here will also be imaginary, so you'll have no x-intercept. However, you can have 1 x-intercept if d is equal to 0, and 2 x-intercept when d is greater than 0. In this case, I present that a is greater than 0. That's why it concave up. And this also a is greater than 0. This also a greater than 0. If a is less than 0, then just to give you a glance, the graphic will have a concave down, just like this. This is a less than 0. Let's move to the next one, which is the linear function. The linear function has general equation f of x equal with ax plus b. The a represent the slope, b represent the x-intercept. So what happened in this case is that the red line will have the y-intercept on 5, and the a value will be positive. The b line, the blue line over here will have the y-intercept equal with 2.5, and the a value will be less than 0. The purple one will have a is undefined, and the green line will have a equal to 0. For this one, it's sometimes referred as y equal with constant, which is in this case y equal with 3. For the purple line, sometimes referred as x equal with constant, in this case x equal to -1. The direct variation function is the simplifications of the linear functions. As you can see over here, there is no there is no y-intercept over here. So I'm going to write the slope sign for us. For the first three solid line, we have the red line represent y equal with x, which means that the a is equal to 1. Lower than that, the purple line represent that the a is between 0 to 1. So it will have a more gentle slope. While for the green line, it will have a steeper slope. Let's continue with the dashed line. For the red dashed line, it will have a equal to -1. For the black dashed line, it will have the value of a is between -1 and 0. And for the blue dashed line, it will have a greater than, less than -1. Okay. The next one is power functions. It has a general equation f of x equal with a times with x to the power of b. This is a simple modifications from the polynomial functions, and you'll not have plus with the other terms. So that's why this is only the power functions. Below the power functions over here, I present three graphs. For these three graphs, I set the value of a is greater than 0. And the b will vary for each these three graphs. For the first graph, b will be between 0 and 1. For the second graph, b is higher than 1. And for the last graph, b is less than 0. This is always also called as the inverse variation function, because you will have y equal with a times with x to the power of -b, or you can also write it as a over x to the power of b. The next functions will be the exponential. It has the general equation f of x equal with a times with b to the power of x. Same like before, I set the a equal with positive value. For the first graph of the exponential, the b is not negative, but the b will have a value between 0 and 1. And then for the second graph, it will have a value above 1. These two graphs sometimes get switched, especially when you look at the shape, which is almost equal. But you can tell the difference between the power and the exponential by looking at their intersections over here. For the power function, it will have the intersection at origin point, which is 0, 0. For the exponential function, it will have the y-intersection on a constant over here, so which is above the x-axis. So I'm going to give you an example how we can have that. Using this condition, I'm going to set the value so we'll understand this more. If the power function is equal with a times with x to the power of b, a is greater than 0, so I'll pick a number, let's say 4, and then times with x to the power of b. b is greater than 1, I'll pick to the power of 3 or 2. So when I set y equal with 4 times with x to the power of 3, if the x is equal to 0, then the y will also be 0. That's why you have it from the origin point. When the x is 1, then the y will be 4, and when the x is 2, then it will be 8 times with 4, which is 32. So it increased exponentially, but this is not exponential. Let's have the exponential and use these conditions. So if I have the exponential function, I'll get y equal with a times with b to the power of x. Let's set the a is greater than 0. So same like before, I'm going to set a is equal to 4, and then b, I'm going to set it as 3 to the power of x. Now if the x is equal to 0, then I will have 3 to the power of 0, which is 1. 4 times with 1, then I'll get the y is equal to 4. So I will not have it from the origin, because I have 4 times with 3 to the power of 1, 4 times with 3 to the power of 0, which is 4 over here. So it will have a constant, which not 0. You can set the example on the other graph also, such as this one. If you put it y equal with 4 times with x to the power of negative 3, since you have b is less than 0, then the equations will be 4 over x to the power of 3, which means that when the x is equal to 0, you'll have the y is undefined, because 4 divided by 0, which is undefined. But when the x goes to infinite, then 4 divided by infinite number, then it will go to the 0. That's why you have the horizontal and the vertical asymptote on this graphic. Let's continue with the rational algebraic function. Polynomial function. The graph will look like this one. It has also removable discontinuity and also the asymptotes, which I'm not going to put detail on it on this section. Beside these names of functions, I require you to understand the other 6 basic elementary functions. So I'll just go through it. The first one is the identity function. This is almost same like the direct variations. The second one is the square function, which is related to the quadratic functions. The third one is the cubic function. This is what it looks like. And then the fourth is the square root function, which is related to the power functions when the a is between when the a is between 0 to 1. Okay, and then you have cube root function. It goes like this. And then the absolute value, which is always above the x-axis for the range. Okay, we come to the end, which is the domain and the range. If I set the domain, and the domain is from negative 2.5 up to x equal with 2, then what is the range? That is the questions. So to locate the range, we have to know the domain. The domain starts from negative 2.5. So let's say that this is negative 2.5, and it goes up until 2. So I'm going to highlight this part. You'll have 3 up and down for this domain. The first one is from negative 2.5 up to 2. The range is varied from 0 up until 1 over here. And then it goes down from 1 up until negative 3, and then it goes up again up until here, which is 17. I'll write the number for us. So you have like 3 value, negative 3, 1, and then 17. But the question still, what is the range? So the range is the maximum and the minimum point. It ranges from negative 3 up until 17. It's not 1 to negative 3, it's not negative 3 to 0 or 1 to 17, but the maximum and the minimum over here. So there we have it. To test if we really understand or not, if I ask you what is the range if the domain is from x greater than negative 2, greater or equal to negative 2, then what you need to do is to list out or mark the graph. So I'm going to erase this for us. We'll have a new one, and then it varied from negative 2 up until infinity. So you will see that the range will be y greater equal to negative 3, not because this is equal, but because it will reach 3 over here, negative 3 over there. So that's it, quite long, but